Hi, I'm going to do a quick video here on data structures in math. This can be some useful stuff to think about when you're making a computer algebra system. Now, data structures. I'm going to be talking about some really simple ones, not the kinds that you're going to see in computer science, but just some simple math data structures. One is going to be fractions. I'm going to give some examples of these. So some examples of fractions are obviously 1/4 is a fraction, and 4/1 is a fraction equals 4. If you want to consider 4 part of this, and it certainly is if you're talking about the rational numbers. If instead of saying fractions, you say rational numbers, then 4 is definitely in there. Another example of a data structure is complex numbers. And some examples of that are I is a complex number, and say 3 plus 6i is a complex number. Make a table out of this. And I'm going to talk about vectors as well as another example. And all of my examples down here are going to be for 3D vectors, but you can have any number of dimensions that you want. So a 3D vector is just a set of 3 numbers, and one example is the vector of 3, 4, and 5, which is also, you can also call that 3 times x hat plus 4 times y hat plus 5 times z hat. There's lots of different ways of writing vectors. Equals, sometimes people use I, j, and k instead of x, y, and z. Plus 4j hat plus 5k hat, where x hat equals I hat equals 1, 0, 0, etc. Y hat equals j hat equals 0, 1, 0, and z hat equals k hat equals 0, 0, 1. So these are just some examples of data structures. And the reason that I call these data structures, I'll put down right here, next thing in our table. The data. What is the data in these data structures? So if I ask you, what is a fraction? Go ahead and answer that. What is a fraction? It's kind of a tricky question, and it depends on what you're doing with the fraction. It sort of depends on who you ask what a fraction is. But we'll probably all agree that a fraction has 2 numbers in it, at least. Or at most, 2 numbers. If you consider this 4 a rational number, and you're talking about rational numbers, then maybe you can say it has 1. But anyway, a fraction consists of 2. Whoops, that's a 3. 2 integers. And they're the numerator and the denominator. So, numerator and denominator. So, and these things, you treat them differently. You treat the numerator one way and the denominator differently, another way, when you're doing things with fractions. So I'll get to that a little bit more later. And then for complex numbers, the data is also 2 numbers. For the complex numbers, you have the real part and the imaginary part. 2 numbers, usually 2 real numbers. But you don't have to use real numbers. You can also use rational numbers to define your complex numbers. So you can have the rational complex numbers as well. But we'll just say 2 numbers, and they are the real part and the imaginary part. So these are data structures again because they're structured data. The data is two integers for a fraction. It's got a numerator and a denominator as the structure. And for a complex number, it's two numbers of some kind, and the structure is that it has a real part and an imaginary part. And then vectors, for a vector, you have in an n-dimensional, for an n-dimensional vector, I'm using 3 dimensions as my example, but you generally have n numbers, which are called scalars in the lingo of vector spaces. And so for a 3D vector, as an example, you have 3 numbers. And then the next thing that you can do with these that's kind of interesting to look at is operations on these things. We have operations on numbers, like addition and multiplication and so on. And maybe I could have put, since these are kind of going from least complicated to most complicated, I could have put another column over here that's even less complicated than any of this stuff, that's maybe like the natural numbers, 0, 1, 2, 3, and so on. And we all know how to add and multiply natural numbers, I hope. But anyway, all of these things have sort of notions of operations that you can do on them, like there's addition. I'm going to go through a couple different operations here. One of them is addition, and here we start to see where the data is structured, where the numerator and the denominator are treated differently in a fraction. If you have two fractions, a over b plus c over d, and you add them, you cross multiply, and you get AD plus BC over BD. And yeah, so that's the answer. That's how you add fractions. Then to add complex numbers, if you have a plus bi and you have c plus di as two different complex numbers, and you add them, then you get a plus c as the real parts. You add their real parts together, and then you add their imaginary parts together, plus b plus d times I. So that is the sum of the complex numbers. And again, well, we treat the real part and the imaginary part sort of in parallel in this case, and same with vectors. If you have a, b, and c as a vector plus d, e, f, then the sum, you just add them component-wise, is a plus d, b plus e, and c plus f. So there's addition, and so you might ask, okay, so these things all add differently. Like, this is clearly different than these guys. These guys all add component-wise. The real parts add together and the imaginary parts add together, and these guys add straight across. But this thing we cross-multiplied in this funny way. So how can you say that this is addition and this is addition when they're different? Well, I mean, there's different ways of talking about this, but you can look up group theory. You can look up, like, modern algebra is kind of like the study of this stuff. Operations on sets. And so that's kind of how you can unify these things and say that, yes, these are all different kinds of addition. So another example of an operation, multiplication. And we'll see where things get a little bit complicated here. I mean, math is big and has a lot going on. So for fractions, if you have a over b times c over d, you just multiply straight across, equals ac over bd. And then, so that's easy enough. And then if you have two complex numbers, also multiplication's pretty easy. If you have a plus bi times c plus di, and you multiply them, then you multiply the real parts, you multiply the imaginary parts and take the negative, because I times I is -1, equals AC minus BD plus the imaginary part ends up being AD plus BCI. So that's just how to add or multiply complex numbers. But vectors are a little bit different. With vectors, there's no really straightforward way to multiply them. You can multiply straight across and say ABC times DEF, just looking up here. You could say, well, that's AD, BE, and CF, but that doesn't turn out to be super useful. There are a couple different ways that you can multiply vectors. One is the dot product or inner product. ABC times DEF equals AD plus BE plus CF, where you multiply component-wise, but then add all of the components together. And this is not a vector. This is a scalar. Going back up to this word here, that this is a member of the underlying scalar field of the vector field. So then this is one way to multiply vectors. There's another way to multiply vectors. I mean, there are lots of ways to multiply vectors. In 3D, you can do the cross product, which does yield another vector, ABC cross DEF, ends up being BF. When you take the cross product, for the top component, you ignore the top components of these, and then you multiply, like in an X pattern, BF minus CE. And then for the second component, you ignore these guys, and it ends up being... You start with the next one down. Anyway, there you can look up how to do cross products. But anyway, CD minus AF, and then we get AE minus BD. So this is the cross product. So there are multiple ways to multiply vectors. This only really works in 3 dimensions. In other numbers of dimensions, you get you can extend this, but you don't get a vector back. Anyway, and you can argue that this isn't even exactly a vector, so to speak. Oh, I mean, there's stuff going on. But anyway, so you can multiply things. You can also take lengths. The length or the size or the magnitude. Which I will write as 2 bars, the magnitude or the size of a fraction a over b is just the absolute value of each. This is now the absolute value, which if I had another column over the left, I would have defined that. But anyway, the magnitude of a fraction is just the absolute value of its component numbers. And then the magnitude of a complex number is just, you can sort of like use the Pythagorean theorem, and this is root a squared plus b squared. And also, you can also come up with a formula where if you use the complex conjugate, where a plus bi complex conjugate is a minus bi, then the magnitude of a complex number, which I'll just write x. Magnitude of a complex number is root of x times x complex conjugate, as you can verify. But anyway, so that's the magnitude of a complex number. Then we can do magnitudes of vectors as well, a, b, and c. If we have a vector, we can take the magnitude and we get root of a squared plus b squared plus c squared. And also you can write this, if you have some vector called x, then the magnitude is just the root of the dot product of x with itself. So there's another example of a magnitude. So you can unify all this stuff, kind of like I mentioned earlier. If you look up modern algebra, groups, abelian groups, semi-groups, etc. This is the branch of math that sort of studies how to unify different systems of numbers and sort of different data structures in math so that you can use an operation that you call, say, addition or multiplication. And the nice thing about doing that is that once you write some code, say, that adds things, then if the way that it adds them is by saying, oh, these things are part of a group, therefore I'm going to add them, therefore I can add them, then you can use that code anytime you have a new thing. If you just say how it forms a group, then you can use that same code. And so things get really extensible then, just by defining how things implement these operations of addition, multiplication, magnitude, and so on. So that's about all. Just sort of drawing some parallels between some different data structures in mathematics, and then pointing out the study of those relationships. So that's all. Go look up some group theory and see how you can apply it to your different forms of numbers in math. See you next time.